Welcome back. Today we'll cover another coordinate system. This one's quite a bit different than the ones that we've studied so far because it's based on the velocity vector. In other words, we take the velocity and we say that, let's define that to be the speed times a unit vector in the direction of the speed. So specifically, just to define all the variables, if we were traveling down some path, and if we start at time 0 and our distance along that path is s, then s dot is the derivative of our path length or the speed. That's like what you would measure on your speedometer in your car. And then et is a unit vector pointing in the direction of motion, as you see here. So we start from velocity, and this is useful in a lot of ways. One thing we'll point out is that you can think of getting the velocity, or if the velocity is the derivative of position with time, and we can think of breaking that into two parts, into dr ds, r is a vector, ds dt. This one's just the speed, s dot. So this tells us then that et has to be the derivative of the position vector with respect to the length along the path. So that's one way we can define it. If we knew what our position was as a function of position along the path, we could take that derivative. Say we had a bunch of GPS coordinates or something. To get the acceleration, we'll take the derivative of the velocity, and so we get two parts from the chain rule. This is the acceleration along the path, and then we have a component where we have s dot times the derivative of the unit vector along the path. How do we get that? Well, one way we can do that is to recognize that it's a unit vector, so if we dot the vector into itself, we get the magnitude squared. This comes from math, where we say that a dot a is just the magnitude of a squared. But so if we take the derivative of this expression, what we will get is det dt times et, and then we'll get et times that derivative. And because we have 1 on the other side, this has to be equal to 0. And now notice, order of operations doesn't matter for a dot product, so this just becomes twice the derivative of et with respect to time times et. And that's equal to 0, or in other words, et dot times et has to equal 0. So the derivative of the unit vector has to be perpendicular to et, and we saw something like that in a lecture a little while ago. Okay, so if we use all of that, the equation that we most often use is in this form, where we have the acceleration, and then we define En to be a unit vector in the direction of et dot, and this is just a constant so that we can have the norm of En equal to 1. So that also happens to be the radius of curvature of the path. So we can picture all of this way. If we go from one point to another, we'll always have the et vector. This will always be in the plane of motion. And in that same plane, we also have En pointing to the center of the path, and rho is the radius of curvature, or the radius that the point would travel out if it was moving in a circle. So, putting all of that together, we get two terms. We get the acceleration along the path. This is the speed squared, and the radius of curvature. So this term here is sometimes called the centripetal acceleration, and it has to do with the speed and the radius that we're traveling on. So let's look at some examples of how to use this. I guess I'll mention really quickly, we can also define a third unit vector that's just the cross product of these two. Usually this isn't useful because notice the acceleration is totally in the ET-EN plane. So if we did compute that unit vector, the acceleration would have to have a zero component in that direction. Okay, here's one example of how we might use this. It's the skid pad test. This is something, if you're not too familiar with cars, it's used to evaluate sports cars. So basically they take a car and drive it around a path. This is a wet skid path, usually it would be dry. But they drive around the path. Well, that's not a very good path. Car would have to fly to do that. Yep, so they drive around the path at a constant radius, and they see what's the highest speed they can achieve on the skid pad, and use that to calculate the acceleration of the car. And they give the car a rating in G's, or in terms of the fraction of the acceleration of gravity. So, suppose you have a car, and kind of like in the Disney movie, you decide you're going to trick your car out with a big old spoiler, give you some extra downdraft on the back, extra traction, right? And now you go out to the pad and you're wondering if you've improved the performance. So you measure that you've been able to achieve 50 miles an hour on a 200-foot radius skid pad. So what would the G rating of your car be then? What would your skid pad rating be? So we can work this out fairly easily. We go back to the equation that we just had, which you'll use so much you'll probably memorize it. The acceleration is the linear acceleration along the path plus s dot squared over rho En. And you're told your car gets to 50 miles an hour on the skid pad, and the radius is 200 feet. So we know that rho is 200 feet. And if you're trying to get the best possible acceleration, you want to minimize this term, or we'll want to accelerate slowly. So this term is going to be 0. So our acceleration, the magnitude of our acceleration, will just be s dot squared over rho. And so we can calculate that. That will be 50 miles per hour. And we'll need to put that into feet per second to make everything compatible. So we'll multiply by 1 hour over 60 minutes, and by 1 minute, which is 60 seconds. And then we'll also convert 1 mile into 5,280 feet. Okay, and then we'll square that and divide by 200 feet. And so that will give us something in feet per second squared. So if you plug all of those numbers in, what you get is that the acceleration is 26.9 feet per second squared. Gravity is 32.2 feet per second squared, so we could say that this is 0.83 Gs. So that's pretty respectable for a passenger car, maybe even a high-end passenger car. A good race car, you know, a performance automobile like a Porsche 911 or something can get 1G or even a little over maybe. So, okay, so there's that problem. Now in part B, we ask the question, well, does it matter if we're accelerating while we do the test? And for reference, we say repeat the calculation when we're accelerating at 10 miles per hour per second. So what that means is you would get from 0 to 60 miles per hour in 6 seconds. So that's a fast passenger car, you know, fast sporty car. Probably most of you have never driven cars that can get to 0 to 60 that fast. A really, really high performance car like a Tesla or a Porsche could do this, you know, in 2.5 to maybe 3.5 seconds. So anyway, this is accelerating really quickly. We'll see how much that decreases our skid pad score. So in this case now, we have a non-zero s double dot. That's our 10 miles per hour per second. And we'll have to do a conversion on that as well. So we'll have to multiply that by 5280 over 3600 to get that into feet per second squared. And so we'll use the fact that the acceleration is s double dot et plus s dot squared over rho en. And now we can take the norm of this. What we want is to know the magnitude of the acceleration to get our skid pad score. And because et and en are orthogonal, because they're orthogonal, you might be able to just skip to this equation. Or we could actually write out s double dot et plus s dot squared over rho en dotted into itself. And when we multiply that out, this would be the magnitude squared, so we need the square root of this. When we multiply that out, the first term gives us s double dot squared. The second term gives us s double dot times s dot squared over rho et dot en. And these are orthogonal, so that's 0. So the only other term that survives is this one, squared. Okay, so if we add all of those up and we do the math, in this case we get that the acceleration is 45.8 miles per hour. So that's only a little bit less than the 50 miles per hour that we got in the last example. So that means that if we're accelerating all out as fast as a typical car's engine can take us, it really has a fairly small effect on the overall acceleration and on the point at which the car skids relative to taking the car in a tight turn. We can generate a lot more g-force doing that typically. So there's an example of how we might use this. Another fun example is related to motorcycles. How does this compare if we had a fast bullet bike? And I love this photo. This is amazing to see these drivers who can get the motorcycle laying down so far. Right, so what kind of a g-force are they experiencing to be able to get the bike down that far? You might wonder, right? So this is another fun example that we can do. So if the bike was just driving along straight, and here's the road. And say the center of mass of the bike was a height h above the ground, then we'd have a force mg here, and then the ground would be pushing back on us, right? So that's the way we usually drive. In an extreme corner like this, we take that center of mass that's still a distance h from the ground, and then we'll replace the ground with the reaction forces. So the ground has to push back to hold the bike up, and the ground has to have a friction force that keeps the bike from sliding away. Gravity is still acting downward, and so this causes the bike to lean at some angle theta. So we can use the concepts of path variables to see what the acceleration might be, and how many g's this bike might be taking as a function of the angle theta. So if we look first at the vertical direction, the sum of the forces in the vertical direction, use the usual coordinate system I and j. So the sum of the forces in the vertical direction has to be 0. There's no acceleration in that direction. So this gives us that negative mg plus n is equal to 0, or just that the normal force is equal to mg. Now if we look in the horizontal direction is where this gets a little more interesting. So here we have the friction force. That's the only force acting in the horizontal direction. And that has to be equal to the mass times the acceleration of the body. And if this motorcycle is moving in a circle, so if we looked from the top and we saw this motorcycle moving in a circle with a path that has a radius of curvature rho, then using what we just did in the last example, we could say that this is equal to the mass, and that also has to be in the inward direction, so that would be the mass times s dot squared over rho. So this would be our acceleration, and we might ask, what's the maximum acceleration that we can have? We can get that by looking at the friction force. If you go back to statics, you remember that the friction force always has to be less than or equal to the static coefficient of friction times the normal force. So mu defines how much friction we have between the tires and the road. And so so for this to be true, we can replace the normal force with mg, and this gives us another equation to relate friction force to mu static times mg. And now if we plug in for the above, let's actually not worry about the path. Let's write this as just the lateral acceleration. That's the magnitude of the lateral acceleration. That's what we're really after. So we replace the friction force with the mass times the lateral acceleration. And the masses cancel, and this tells us that our lateral acceleration has to be equal to mu static times g. So typically we think of mu static as being less than or equal to 1, but that's not strictly true. If you have a really sticky surface, it can actually take a force larger than N to get it to slip. And that actually ends up being true for cars. I guess for a lot of years, the best cars you see would have a lateral acceleration in G's being, about 0.9 or 0.95 G's. But if you look at some of the best cars today, sometimes this number can even go to about 1.25. So you can get a much higher acceleration than gravity going through hard corners. Okay, so anyway, that's a fun little example. Notice that we treated the whole thing as just a particle. The whole bike, we're pretending it's a particle. And we're neglecting the angular velocity, the rotation of the wheels, of the engine. And we'll see that those things can also contribute. So we'll revisit this example later and look at this in a little more detail later.